bienvenidos a esta nueva edición del Seminario de Investigación del MODEMAT. En esta ocasión tenemos la participación de José Iglesias, él es investigador en el Bregman Institute de Linz, en Austria. Con José nos conocimos hace 2 años ya, iba a decir el año pasado, pero creo que el 2020 no cuenta mucho, en una conferencia en Cambridge, y bueno, vimos que hay una coincidencia en temas de investigación. Y bueno, José, muchísimas gracias por aceptar nuestra invitación. Y nada, la audiencia es tuya, por favor.
Pues sí, muchas gracias por la invitación. Y si podemos encontrar puntos en común para los que colaborar, yo por lo menos estaría encantado. Y bueno, no sé si debo disculparme, pero la charla va a ser en inglés, porque ya son muchos años de estar en otros países y al final ya hay muchas palabras que no me acuerdo de los temas en sí. So, yeah. So what I'm going to talk about is, well, the title is Geometric Convergence in Total Variation Regularization. And the context is we're looking at an inverse problem, a linear inverse problem, and it's in the simplest possible setting, which is I have an operator equation, which is in some infinite dimensional space. And what you have are measurements. My notation is a little bit strange because I have some ideal measurement that you don't really have access to, and then some noise, which is just some deterministic function. And what you have is really both of these two things together. Just for the analysis, it's easy for me to split the noise, so that's why I write it like this. And what you want to do is find a solution of this operator equation, and this operator is maybe something compact, for example. So it's something that is really smoothing the input. And this will mean that in terms of inverting it, that it will be ill-posed. So the effect of this noise, of this W, will move the input that you get, or the solution that you get for the equation, a lot. And the context will be for real valued functions that live in some d-dimensional space. And of course, if you have something ill-posed, you need to inject some a priori information into this problem to get something reasonable. The assumption that we'll have is the standard one for total variation, which is that the true data, which we will call U dagger, that we want to recover, consists of objects which are separate in some sense. So what I call objects is something like smooth areas which are separated by sharp edges that might be discontinuous. And some applications are things like image deblurring and recovering of inclusions from radar measurements. In both of these cases, you have some operator which is smoothing to different levels, but still smoothing. And there is an operator which is non-trivial. And the way we are going to do this is by, well, posing some regularization functional, which will look like this. You will have this operator, which is bounded and linear, and it will live in this space. This space will be important for me. I really need to do LQ of this domain, and then you measure somewhere else. I'll leave it very general here. It will be some Banach space. And also you have an exponent which goes in the norm of the fidelity term. And then you add some regularization parameter and a regularization functional, which of course it will be the total variation, even though I don't specify it here yet. And what this does is just balance the information coming from these two terms, trying to stay true to your measurements and also not have a too high value on the second term. And yeah, I said this, the spaces that I need to work here, because here it's not just something about function analysis. This is usually the setting of most regularization theory for inverse problems. I really need some real analysis, which happens only in LP or LQ of functions on a Euclidean space. And this is not always with Q equals 2. That's why I leave the exponent. And generally, I will put this exponent in the norm just to be 2, just to make the formulas a little bit simpler. So you could ask yourself, if you start from first principles, what kind of regularization do you want to pick for such a problem? So if you say I want to be smooth, you will want to penalize some kind of derivatives. But at the same time, you want to be allowed to have discontinuities. So a very standard 1D example, you could say let's work in the interval from 0 to 1. And let's consider these three functions. Have this v1, this v2, and then really a step function. This is really going south, discontinuous. If you look at the L2 norm of the gradient, then the faster you go, the greater your norm will be. And if you go to the step function, then this doesn't exist. This is infinite. However, if you just look at the L1 norm of the gradient, in both cases, since the derivative is positive, this is really just how much you went. So this is really, this is invariant to how fast you're actually going up, as long as you are monotone and start and finish on the same values. So this could tell you that perhaps you want to have your regularization functional to be the L1 norm of the derivative. So, and in this case, you would also expect that the step function has value 1 for such a thing. But what does this actually mean? Because this derivative doesn't exist, at least as a function. So the actual definition is, at least in an infinite dimensional space, is to call the total variation the norm of the distributional gradient as a vector valued random measure. So you have to consider distributional derivatives, a distributional gradient. And what you do is test with all vector fields, with the divariances or vector fields which are smooth, compactly supported, and with length, pointwise length, bounded above by 1. So this is a definition by duality, right? And if this is finite for some function, let's say in L1 log, then we say that U has bounded variation. And then you have a space of these functions, which is some Banach space. And if these functions were smooth, like really smooth, then this is really the L1 norm of the gradient. And with this definition, what you can also do is consider the indicatrix of some set. Like, for example, this disk here. If you have 0 outside and 1 inside, you can define something called the perimeter, which is the variation of this characteristic function, this indicator. And if you would have this ball, as is pictured here, you get that the variation of this characteristic function is really the length of the boundary. And the optimal vector field that you will pick is something that aligns at the boundary. So you're really measuring length of a set by the divergence theorem. And this set might not actually exist, but at least in the limit, it will look something like this, prolonged all the way inside. And in fact, this set could be very bad. I mean, this E could be very irregular, but still you have some notion of a length of the boundary. And in particular, you can have formulas like this, in which if you have two sets, this A and this B, then the way you count when you do these intersections is the same way as you would count the boundaries of sets, if they were smooth and this was just normal length, or area if you want, depending on the dimension. And this could actually be an inequality if you have some kind of tangential contact like this. Okay, so we just pose a regularization functional, and at least in my community, let's say in the Austrian community of English problems, the very classical question is, well, what happens when you have very little noise and very little regularization parameters? So are you consistent with getting solutions of the original problem? And for TV, the basic convergence result you can have is if you have, well, your regularization parameter and your noise are disappearing, and you have a quadratic parameter choice, so with these two here, and you say, well, I'll just call this to be a little shorter, the minimizers of my functional, assuming they exist, which you can also prove easily depending on the Q. And in this case, with this parameter choice, just by making obvious bounds like testing with U equals 0 and so on, you have that up to a subsequence, because you need to use some kind of compactness, that the sequence converges to some limit weakly in this space, which is exactly where VV is embedded. So which is something like Sobolev 1, at least in terms of exponents. So this is just Sobolev embedding. And this limit is a solution of the original equation with minimal total variation. And also you can use, instead of weak compactness, you can use some kind of Rayleigh-Kondrakov. So by losing a bit of exponent, you will be able to improve to strong convergence. But if you say, for example, you said that your original Q was exactly this exponent, which is the one that makes everything easier, then even to get this convergence in the original space where you define everything, I mean, you are trying and you cannot, because you lose a bit of exponent to even try to find a convergent subsequence that goes to the limit. So in terms of having something consistent that works in the same spaces and it's getting you to where you want, it's a pretty bad situation. And a second question that is usually asked in this area is, well, if you know you converge, which we don't converge very well here, but we converge in some sense, you could ask, how fast do I converge? And the classical, typical result is that you have linear convergence rates in terms of something called the Bregman distance that I will define soon. And assuming something which is called a source condition, which in this context looks like this. It means I have a source element, which is this P0, to which you apply the adjoint of your operator, and this needs to be in the subgradient of the total variation as the ideal solution. And with a linear parameter choice, so you need to regularize even more to be able to prove this kind of result. And what are these concepts that I had just now? If you have some function, some real valued function that lives in some infinite dimensional, let's say some Banach space or something like this, you can define the subgradient, the convex traditional subgradient, which lives in the dual of this space. And you say that some element is in this subgradient if and only if, you could say, you can see this as in these images here, you look at your point, these are the slopes of hyperplanes that touch your graph from below. And if your function is not differentiable but convex, you could have more elements in the subgradient, but all of them, they fulfill this role, like in this right picture here. And what's very nice is you can characterize minimizing any reasonable unconstrained problems, at least in the convex setting, by saying that 0 is in the subgradient of your function at the optimal solution. So this is just by saying, this is the analog of saying, well, if the derivative of f is 0 when I minimize, like sufficient condition. And actually, since you are convex, this is also, you can also go back. So this completely characterizes minimality. And this Bregman distance that we had is if you have this element that appeared in the subgradient and you apply the adjoint to it, then you can define some sort of a distance, which in some sense is telling you how far you are from being a subgradient at that point. But the problem with this is, well, you might prove all the theorems you like, but the definition of this distance, or this Bregman divergence, it's often called, it's defined in terms of the function itself. So this doesn't give you anything in terms of the norms, unless you have strong convexity, but you have a functional which really looks like this. We are working with something like a L1 type. The only exception that I know of is actually a recent result of Tuomo Valkonen, which you probably know well, which is that convergence rates in norm are actually possible if one is a little bit smarter and uses both terms at the same time, not only the total variation as here. So I mean, this inequality here is not very useful. I mean, you cannot put a norm here. But if you use both terms and you try to combine information from the total variation, which this is to make some kind of Poincare inequality, and some ellipticity of the functional, trying to compensate everything, you can get convergence rates. This is a very strong condition on your operator, so maybe this is not so practical, but it is possible. So in any case, the point I want to make in this talk is a different one, which is I I want to say that I don't even like the norm. Why? Because my justification to talk about total variation was talking about objects which live in your image, something which is sharp. And if you have convergence in LP norm, then I claim that this is not very adequate for measuring shapes of objects. Why? Because if you have something like these two disks here, and you consider the difference of them and you measure it in LP, what do you get? You get the area of the difference, right? Because the values are just 1 or 0. So you get this gray region here that you're counting. And here in this left situation, I would say that these objects, this U and this V, for me, they are very close because they are close everywhere. They look very nice. However, if I look at the situation on the right, here the gray area might be very similar, but this U is very far away from V, like let's say in a perceptual sense. So what's a metric that can characterize this in a reasonable way? What you can do is you can define what's called the Hausdorff distance, in particular the Hausdorff distance of the boundaries of these sets. And what you do to construct this distance is you say, well, I find the distance from a point to the other boundary, and then I take the supremum over all the other set, and then I symmetrize the whole thing because these things are not symmetric. And for this example, you really get something which is more reasonable. On the left side, the maximum is only this little distance between these two, whereas on the right, you're really extremely far away. And this can be seen as some version of geometric version of uniform convergence. And what we would like to do, which is what we are trying to do here, is have it for the boundaries of level sets of this image. Because I said, well, level sets are something like these objects. They are. And yes, and one thing that you can notice here is these two circles. Well, they are circles. But this blue set, to be far away, it needs to have without having a lot of area that is getting out, needs to have a lot of curvature at some point. And what's the relation between curvature and this total variation regularization? I mean, you could just try to take a derivative in the original functional, really starting from this in a completely formal way. And what you will get something depending on the data term with the adjoint, at least if your measurement space is L2. And on the right-hand side, you get something which is like the P Laplacian with P equals 1. And if everything is smooth, then this is actually the mean curvature of the level sets. So of these sets here. Either upper or lower, that doesn't really matter. However, we introduced this whole thing to talk about discontinuous functions. And so this is really very far from a typical use case. Here I just made some simple numerics and some example. I said, well, let's take a blurry image. I know what the kernel of the blurring is. And I try to deblur. And if I say, okay, this had only two values to begin with, so 0 and 1. And I'm trying to find this shape, let's say. So the way I define my recovered shape is, well, let's look at the value just in between, just half. But precisely what I'm trying to recover, and if I want to talk about curvature of these sets, is across this red line, which is the threshold that I put. This is discontinuous. So of course, all of this computation makes no sense. The gradient doesn't exist, and on the two sides, it's 0 anyway. So what can you actually say, which is rigorous, is, well, you go to subgradients, you go to the convex version. And here you have something like the duality mapping of Y. It doesn't really matter what this is. For my purposes, I just hide this in some function, which belongs to the subgradient of TV. Fair enough. And what does it mean to be in the subgradient of TV? Well, yes, this. You can rewrite it as this kind of inequality, which needs to be satisfied for every function in L2. So here it's in a Banach way, but it's the same as in L2. Okay, so, and in the previous slide, I had some curvatures of the level sets of my functions, right? So what does this now? So these subgradients have to do with level sets. So what you can do is express all of these quantities, both this total variation and these integrals, in terms of integrals over the level sets. This is done on the one hand with what's called the coarea formula, which tells you that you can look at the perimeter of your level sets and recover the variation of the function. So this is the same as the this is the more dimensional analog of the picture that we had that told us that the variation doesn't really care about how fast you are going up. And the other one is this version of Fubini, which just tells you, well, you can compute integrals of functions just by slicing them like this, at least if they're positive. So you just need to take. And after a little bit of work, what you can do is you end up with something like this. You say the level set of your denoised image actually is a minimizer for some problem which is made over finite perimeter sets. Finite perimeter sets just saying that this term is fine. And well, it looks like this perimeter, so length of the boundary minus some integral term inside this set. And this is a definition which I didn't invent. Some other people made this name, which is to say that of this set. So if you are a minimizer of this functional, then you have a variational curvature, which is whichever function you're integrating here. And if everything was smooth, this would mean exactly the same thing. Just by taking variations here, you would say, well, let's take a perturbation of my set, move it a bit like this, and you will end up with variation of the area, mean curvature, and here just how much you are. On the other hand, this is a bit of a strange concept, right? Because I'm using the word curvature for this function, which actually lives on the whole domain for the boundary of something. So this is somehow almost by definition not unique, because you could have a minimizer which lives somewhere else with the same curvature, which is fine. And it's also in some way quite non-local, because you are moving everything to inside the set, since they are defined with really volume integrals. However, if you look at this functional here, it can start to tell you something about what your problem wants to do or what your level sets want to look like. Heuristic that you can make is if you were able to have a control on this function in this space, in LD, at least locally, if you say, well, will this want to make, if I add a little ball to my set, so it looks like this, and I add a small ball, will I gain energy or will I lose it? So this will depend on the competition between this term and this other term. So you gain some perimeter, which goes like r to the d minus 1. And precisely because of this norm here, this LD, you can make a Hölder inequality, and this goes with the same rate. So depending on this constant and that constant, you will be able to control that you don't want to make something small, if r is small enough. And this is actually what will the basic idea of why you will not want to, well, you will have this kind of convergence, which is uniform, which is not making some small structures that are doing something weird. And if you would assume that these UNs have a common compact support, so that you don't care about this log basically, then the original thing you had is just convergence of the area, of the difference of these two sets. But to improve to Hausdorff, what you need is to say that they are not sharp tips or small components like the ones we had before. And the formal statement is some kind of weak regularity that you need for these sets. What you will need to prove is that there is some radius, such that if you put a ball anywhere on the boundaries of these sets, and a constant, such that when you compare with a ball and you say, well, which part of the ball is inside the set and outside the set, they should be bounded below by something which is bounded away from zero. And you will get this convergence that I have mentioned quite easily if you are able to prove this uniformly in n and uniformly in, well, in the point and all along the sequence. So this says that these sets are not getting more complicated. Okay, and actually we didn't completely start with this topic. This was started by, in this very interesting paper of Sambol and co-authors, in which they started doing this for the noise. So, and our business was been trying to stretch this as far as possible. So doing it with inverse problems, with higher dimensions, with bounded domains, and even without source condition, we have some results now. And the strategy to prove this is, well, first you notice that your dual lives in LQ star, which is, and it actually also involves this V that we had before from the subgradient. And this should belong to LB. So this tells you that essentially you want to have this exponent. And this is, for me, this is not necessarily 2, it could be more. So that's why I need different exponents. And then you look at what these dual variables are doing. First, you say that if I have no noise, then they are going strongly to something. And if you have noise, then you can prove some kind of stability estimate that needs to be explicit. And with both of these, you end up with this regularity that I just mentioned. So if you look at the dual problem, the Fecha dual of what you started with, and using this characterization for one homogeneous function, it tells you that the subgradient at any point is always characterized with the subgradient at 0. So you have this set that you're moving around. Then directly the dual of your problem would be to maximize among elements in the dual of the measurement space, which are constrained to be in the set that you're moving around, this quantity here. So you are trying to align your measurement with this variable that you're minimizing over, compensated with a little bit of norm. So this looks a bit like a pre-X. And since A is continuous and you have just a norm somewhere, you have strong duality. This is the easiest constraint qualification you can have, right? And so the infimum is the supremum. You already knew or assumed that you had a minimizer here, and in the dual you have a maximizer as well. And the optimality condition is, well, exactly what you had before. So you have this function B, which if you would compute what goes here, is exactly the same. And so I said, then I want to know a little bit more about this dual. So one thing you can do is, I had this quantity here, and I was maximizing it. So what I can do is say, well, I'll write minimize. I multiply by something which is negative. Didn't change the minimizer. Then I add some term which has nothing to do with the variable that I'm minimizing over. So I add this in here. And I have this equivalent problem that has the same solution. But now, if you look at it, this looks very similar to this formula here, when I wrote here for a Hilbert space, in which you have, well, norm, inner product. So you could try and complete the square, let's say, and realize that at least in the Hilbert setting, this is really projection onto some convex set. In the Banach setting, you cannot quite do that, but I mean, this equality here is not true, right? But still, with the left-hand side, with really the same problem that we had, you can still prove some kind of stability, because of course, projections onto a convex set are not expansive, so you get an inequality immediately. With a little more work, you can still do it in this Banach setting, and now what appears in your inequality has to do with the uniform convexity of Y star. So this is a modulus of uniform convexity for the norm of the dual square. So if you assume that the space is vaguely reasonable, your balls are a little round, which is what this uniform convexity means, you still get this estimate, which relates this dual variable with noise and without noise. Here is with this piece, you can apply the adjoint and get the other dual variables and still get the same kind of estimate. And if I have control over the ratio of this linear parameter choice, that will be because you have noise over parameter regularization parameter, you can make this as small as you like. Very good. So that was one of the parts. The other part to this was looking at these variables without noise, right? And if you would just put everything to 0, the formal limit that you will get for your problem is, well, on the one hand, minimize the total variation among exact solutions, which you assume they exist. And the same problem you had is align your measurement to the dual variable, but without the norm term. Now your first term became a constraint because you made the parameter go to 0, this alpha go to 0 or infinity in the other one. So you don't have strong duality anymore. But exactly if you assume the source condition, if there is this P0 that lives in the subgradient, then this exactly means that this problem has a solution, like this, because these functions are one homogeneous. And this also gives that the noiseless P alphas, so these dual variables, but without the noise, they converge strongly to the subgradient here with the minimal norm. And this is again by the same kind of problem. So you just compare this problem with the previous one, change the solution, test with the solutions of the other one, and you will get exactly this. Again, for spaces that are relatively recent. And the consequence of all of this is you look at, if you look at these curvature variables, the dual variables that you have, and you say they converge strongly and they live in LD. So that's pretty good because you have this kind of what we call equiintegrability. So for each epsilon, there is some size such that the integrals of the diff powers of these functions are not big. And this goes very much in the direction that you want. And to actually prove the estimate, what you do is, while you compare in your minimization problem, what you will get is a formula like this. After a little algebra, you get that the area of what you took out by testing with a ball and removing it is bounded by this green part here. Well, this difference of these two things is bounded by the green part. And actually, if you think a little bit about it, the way this is written, it's, I mean, if you look at this, if you do something like polar coordinates, this is actually the derivative of the area as you go in the radial direction. So you really get this. Okay, and this second term you have, this integral, you can say, well, I do Hölder inequality, then I separate the noise because I know how to control the noise and the ones without noise. Both of them are small as you want by your parameter choice. Then you can do an isoparametric inequality to relate this perimeter and the area. And what you get is some differential inequality really on the same quantities, which is exactly gives you what you want. Which was this density estimates that say, well, the fraction of area is controlled. And this can also be done with boundary conditions. You just need to use slightly different inequalities. Let me just be fast there because it's not so interesting. And first, we assume that we had a compact support. You can also prove this in a similar way, just saying, trying to control what escapes to infinity. And what you end up with is, well, for the Q, which is the right one, for domains in general, and with a linear parameter choice, which needs to be above a certain constant, which depends on everything in a pretty not explicit way, and with the source condition. And the source condition has actually, this U dagger maybe is not unique, but it doesn't matter. If you have the source condition for one of them, you have them for all of them. Then this, at least the subsequence that converges that you had, you can improve the convergence such that you really have the better convergence, which means that you are uniformly close in the geometry. So the objects you see are really close as you go to the limit. And actually, since you are saying you have no small components in everything you're doing, you have no small structures that they created in the problem, you can apply this also, let's say, in the vertical direction, which is, well, how do you make a function which is integrable but is unbounded? So it, of course, as you go up in the value, you will need to get something, you will end up with something small. But our estimates of no small structures, they are uniform in everything. They're also uniform in this direction. So eventually, this is forbidden, and you will get a limit of how far up you can go. So you get an L infinity estimate for all of these functions at the same time, which again depends on everything. And if you had convergence in L1, then you can also improve to convergence in any LP norm, including the LQ that you started with. And this is not completely trivial, because if you are doing something which is not denoising, then, well, first the noise could be unbounded, which is a little bit strange. If your system has some bounds in what you can measure, then not. But even if your measurements are bounded, then, well, it doesn't mean, if in this functional setting, that the most likely explanation through the operator is really bounded as well. And this bound is really not explicit in any way, because you are using the equintegrability of this. So I cannot tell you what this number is, I can only tell you it exists. And if you look at a quick numerical example, then it will look something like this. Here I have a sequence of noisy images, or convolved with the same kernel and then adding some noise. Then I apply total variation regularization with a not optimal parameter, but in a way that the parameter goes linearly with the amount of noise, which is exactly the same here. And as you lose noise and as you regularize less, then you see how the level sets get close to the limit in a uniform way. And well, it's getting a little bit late. So just as a short remark, actually the whole thing, the main assumption here was the source condition, which was something with the subgradient of the total variation at the limit. And this is not totally satisfactory, because in many situations that you could think of, like for example, the characteristic function of the square, so this is as usual 1 and 0. This limit, if u dagger is this, then actually in L2 the subgradient of the total variation is empty. And this has to do with the corners here. However, the theorem that you wanted to prove, that you go in Hausdorff convergence and all of this is all completely true. Just the method of proof is not good enough. So the question could be, can you avoid the source condition? And our answer so far, and this was already hard to do, is we can do it, but only in that setting, which means only for characteristic functions, for indicatives. And even if the subgradient is empty. So without source condition, you can still do something, which becomes quite more complicated. So instead of having the A star of P0, which is somehow your limit dual variable that you need to do things with, there is work in this area of these variational curvatures, which can, someone already told you that for any set, you can construct something which actually lives in L1, which is not the dual of anything, but it exists. And really looking pointwise at what this function is doing, you can still make this same kind of result. And these density estimates that you had are not uniform anymore. So as you get close to the set, your solutions are getting more complicated, but you have a bound of how far you can be. And combining these two things, you end up with the same cut of convergence. Okay, and just to conclude, yes, my main points were for TV regularization, your dual variables have something to do with curvatures of the level sets. In more dimensions, you cannot work in L2 to do this kind of results. And here's a little sketch of the proof. And the source condition can be bypassed for really characteristic functions that we're able to do right now. Maybe it's possible, but we don't know how. And this is just our papers on this topic. It's for advertising. And thank you for your attention. That's all.
Muchísimas gracias, José, por esta interesante charla. Y llega el tiempo de preguntas.
Bueno, gracias por escucharme.
Por favor, preguntas, comentarios. Pues yo tengo uno que es más una curiosidad sobre el tema de la implementación numérica. ¿Con qué métodos? ¿Son métodos de level set los que utilizaron para el ejemplo numérico?
No, esto en realidad es en la otra dirección. Es decir, por ejemplo, lo que he computado aquí, esto es Chambol POC, esto es completamente estándar, con diferencias finitas. Es decir, mi punto, lo que intento decir es que podemos tener propiedades de los level sets sin tener que hacer algo sobre level sets numéricamente.
Ok. Sí.
Es decir, va un poco en la otra dirección. Intenta juntar las dos cosas, pero a nivel práctico, esto simplemente son métodos de optimización convexa estándar. Es decir, todo lo que ya conocemos.
Ok, gracias. Juan Carlos tiene una pregunta, porfa.
Sí, bueno, ¿qué tal, José? Muchas gracias por la charla,
Muy
en
bien, gracias.
efecto, muy interesante. Es un poco una curiosidad también por el lado del tema que hacemos nosotros o que trabajamos bastante, que es este modelo de Mosolov para los fluidos viscoplásticos,
Sí.
que básicamente en el caso sencillo, no sé si lo conoces, tiene
Sí.
este gradiente al cuadrado. Y yo no sé si es que, o sea, es básicamente lo que tienes en tu problema, pero aparte de eso tienes esta norma del gradiente al cuadrado. Y no sé si es que han tratado, porque sé que Scherzer también tiene algún trabajo con ese tipo de modelos.
Sí,
Y no
yo
sé si
también he
han tratado de extender y eso.
trabajado en ello, sí.
Ya, entonces si nos puedes contar un poco si es que se extienden o algo por el estilo.
Relación con esto es un poco complicado, porque aquí, es decir, el tema central para todo esto que he presentado es la relación entre la variación total y estas integrales que son simplemente de una función, de algo sin derivada. Entonces, la relación entre la variación total y el término de viscosidad, digamos, para ver si quisiéramos ver algo sobre cuando me acerco al límite, cuando el flujo se va a parar, por ejemplo, tendría que saber algo tendría que tener algo muy detallado sobre la relación entre el término de variación total y el término de viscosidad. Y eso la verdad es que ahora mismo no sé cómo hacerlo en absoluto. Sí, sería muy interesante, pero ahora mismo no tengo las herramientas por ahora.
Ya, dale, gracias, porque sí hay este artículo original del 50 y tanto, ¿no? Que es justo el del
Sí,
modelo donde algo estudian ese núcleo y esa cosa, y claro, es muy interesante cómo lo hacen ahí, pero me imagino que son técnicas ya muy viejas, ¿no?
Sí. Es decir, me imagino que se puede hacer un resultado del mismo tipo, en el sentido, es decir, cuando todavía está fluyendo, cuando todavía tiene una viscosidad y el fluido de verdad se está moviendo, también tiene esta parte que no se mueve en el medio.
Ujú.
Es decir, si es una tubería, pues en el centro tiene la parte rígida, o el plug, que se suele llamar, o tiene diferentes nombres. Y me imagino que uno sería capaz de, según el fluido se para, al llegar al critical yield stress, o al yield limit, el YC típico, de ser capaz de ver este mismo tipo de resultado. Es decir, la forma de este plug se acerca a la del límite de una manera uniforme o tener más información sobre realmente esta geometría. Es decir, me imagino que el resultado es cierto, pero cómo demostrarlo ahora mismo no lo sé.
Dale, gracias, José.
Gracias, Juan Carlos. ¿Alguna otra pregunta? Bueno, sí, de hecho con José estábamos conversando sobre la posibilidad de arrancar alguna colaboración con problemas de inversos relacionados con Bingham, así que de hecho estábamos ya en esa jugada. ¿Algún otro comentario, alguna otra pregunta, colegas? No sé. Bueno, entonces, si no es el caso, José, nuevamente agradecerte enormemente tu participación, el haber aceptado nuestra invitación. Bueno, invitarte también a las charlas del seminario que las hacemos semanalmente. Y dale, ojalá en algún punto esto ya se compone la situación y podamos tenerte en vivo y en directo en Quito en algún momento.
Sí, de hecho, si hay alguna lista de correo, me podéis mandar los mensajes regularmente, me encantaría.
Seguro, perfecto, seguro. Listo, bueno, muchísimas gracias entonces. Gracias por su presencia, colegas. Espero que tengan un buen fin de semana y nos estamos viendo en la siguiente sesión del seminario. Gracias. Adiós. Cuídense.
Muchas gracias.
Chao,
Cuídense.
gracias.
Bye bye.
Chao, José. Gracias. Adiós.